In this session, we'll continue exploring R and we'll introduce some of the fundamental concepts and vocabulary terms that you'll become very familiar with. The first thing I usually do when I open up R is create a new project. This way I don't have to mess with the working directory because the project directs R to the folder where we'll be working with. So let's go ahead and create a new project, select new directory, new project, and I'm going to give this directory name Intro to R. And I'll create it as a subdirectory of my course folder. And it takes a minute to restart the session. And now I can see I have this .r project file and I'm ready to go. So let's explore some of R's capabilities. You can use R as a basic calculator. It's basically a fancy calculator by typing code directly into the console. So I can type 3 plus 5, and when I select enter, I get an output. I can also do 12 divided by 7. When I select enter, I get the output. The order of operations that are run in R follow the mathematical order of operations. However, to do more useful and interesting things, we want to assign these values to objects that we can use later on. So to create an object, we need to give it a name, followed by the assignment operator. I'm going to call this object weight underscore kg for kilograms, and I'm going to use the assignment operator. So in R, the assignment operator is this Pac-Man less than followed by a dash, and you can, a keyboard shortcut on Windows is Alt minus, and in a Mac, I believe it's Option minus at the same time. As you can, you don't have to do the whole less than followed by a dash. You can do it in a single stroke. And let's assign weight kilograms a value of 55. When I select enter, now there's no output, but there's this weight object in our environment. So it's stored within our session. This assignment operator can be read as 55 goes into this object here, weight kilograms. It's important to know, especially if you're looking up how to do things in R by yourself, that you can replace the assignment operator with an equal sign. They're equivalent, but it's better practice to use the assignment operator because once you get into more advanced functionalities of using R, this equal sign can have different meanings. It's good for you to know that you can substitute them, but it's also important to be aware that the preferred assignment operator is this symbol. And again, that's Alt minus or Option minus. You can give objects any name, like X or temperature, but you want your object names to be short, descriptive, and concise. Object names in R can't start with a number. That confuses R, and R is also case sensitive. So weight kilogram, all lowercase letters, is different than weight kilogram with a capital letter. Okay? If I call the object using all lowercase letters, I receive the value of that object. But if I call the object with a capital W, R returns this error that this object was not found. And in some cases, when you see an error and you don't think there should be an error, everything looks right, it's usually because of a typo, that there's some case sensitivity going on. It's important to be consistent in the styling of your code, and because this makes your code clearer to read for your future self when you come back to that code, or your collaborators when you're passing along that code. We've been calling this an object. So what are known as objects in R are known as variables in other programming languages. In this lesson, the two words are used synonymously. When assigning a value to an object, let's call this, maybe it's 75 degrees this morning. When assigning a value to that object, notice that R doesn't print anything. If you want R to print something, you could force it to print by assigning that object inside of parentheses. You can also return the value of that object by typing in the name of the object. In R, we'll find that there are many ways to do the same thing. And that's both a strength and a weakness of R, especially when you're learning. Having all these options is sometimes challenging. But as you get more fluent in R language, then having these options is actually an advantage. So now that R has these objects in memory, we can do arithmetic with them. For instance, we may want to convert this weight in kilograms into pounds. And we know that weight in pounds is 2.2 times the weight in kilograms. So we would multiply this weight kilogram by 2.2. If you notice that these option boxes pop up when I type the name of the object and it matches something in my environment, then R will create this pop-up box which I could use the arrow keys, and I'm going to highlight the object I'm interested in and select the tab. So that's a tab autofill. What this does is help reduce the amount of typing and thus typing errors. So let's go ahead and run this code, and we see now we have our weight in kilograms multiplied by 2.2, and the value is 121. Now we didn't store this inside of an object, which is why R returned the value itself. We can also change an object's value by assigning it a new value. Let's store a new value inside this weight kilogram object. Let's say 57.5. I'm going to select enter. And now when we multiply weight kilogram by 2.2, R returns the new value, right? Using the new value that we stored in weight kilogram. Notice how it overwrote the previous value. Let's store the animal's weight in pounds in a new object instead of printing it out here. So I'm going to create a new object called weight in pounds, and inside that object I'm going to store the value 2.2 times weight kilograms. All right, so we see this. Let me expand these here. Now we see that object stored. Now let's change weight kilograms to 100. And we see that this value has changed here. So what do you think is the current content of weight pounds? Do you think it's 100 times 2.2, or do you think it was the previously stored value? If you said it was the previously stored value, you're correct, because we didn't rerun this line of code, and so R assumes that it's the same, which it is. So notice how if we wanted the updated value, we would have to rerun this code. And what I did there to get to that line of code is I put my cursor, my blinking cursor, on this Pac-Man symbol. Remember, that means that R is ready and waiting for a command. And I selected the up arrow. And every time I select the up arrow, it goes up a line in the code. This helps to reduce the amount of typing, reduce the amount of typing errors. So to get this updated value of weight pounds using our new value of weight kilograms, I would have to rerun that. And notice here that how this will change from 126.5 to 220. Up to now, we're writing code completely inside of the console, and this is useful for quick queries if you're trialing and error things. Maybe you're testing stuff out from the help examples, right? But it's not so helpful if you want to revisit your work for any reason in the future. To open a script, you can select Control Shift N. And another alternative is to use this icon to open up a new R script using that Control Shift N. If you're on a Mac, then you'll see the keyboard shortcut is probably Command Shift N. When you open up a new script, you'll want to save this. You can use Control S keyboard or select the floppy disk here. And I typically save my scripts as the same name as my project, but there's instances where you might want them to be different. You'll want to, as you begin typing code, you'll want to save your work periodically, just as if you were working in a Word document, you repeatedly save the document so you don't lose your work. Let's talk about comments. Comments in R are created by using the hashtag character. You can enter however many hashtags you want. The comment character creates anything to the right of this hashtag will be basically ignored by R. And it's really useful to leave notes and explanations in your scripts to help you understand what the code is doing, or when you pass your code along to other people to help them understand what each section of code does. RStudio makes it easy to comment or uncomment a paragraph. After selecting the lines you want to comment, press at the same time Control Shift C to uncomment that line. If you only want to comment out one line, you can put the cursor at any location of that line, then press Control Shift C. So Control Shift C allows you to toggle back and forth. So I'm going to create a comment. Comments help understand code sections, something like that. Let's go ahead and talk about functions and their arguments. We saw a preview of functions last week, but because we hadn't gone through it, you probably wouldn't have recognized it, and that's fine. Let's go into more detail now. Functions are the primary kind of built-in scripts inside R that automate more complicated sets of commands. Many functions are predefined and you can access them by importing different packages or libraries, and we'll talk more about that later. A function usually takes one or more inputs called arguments, and functions typically return a value. An example of a function would be a square root. So I'm going to create an object called I'll create an object called weight kilograms, like we've been working with. And inside of that object, I'm going to use the function square root. So that's the function name. And they're usually always followed by these parentheses. And inside the parentheses is where the arguments or inputs go. So in this case, the argument must be a number. So let's say something like 16. And the return value is the output. So I ran that line by putting my cursor on that line and selecting Control Enter. You can also put your cursor on that line and select Run. So now if I copy and paste the object name here and select Run, then R prints out the output value. So executing a function or running it is called calling that function. A lot of new terms here. Don't be overwhelmed. You'll start to pick up these terms the more and more you practice coding in R, the more you learn about R. So the square root function calculates the square root and returns the value, which in this case was assigned to the object weight underscore kilogram. And this is an example of a simple function because it takes only one argument. So let's look at the help file for this function, and I'll expand these a little bit to make our viewing easier. And we can see examples of the usage and what arguments go in. So in this case, the argument requires a numeric or vector. And we'll talk about that next. You can also see the arguments by once you're typing the function, and here we see the drop down box again. Here you can see this yellow information box gives the argument. So it takes a numeric value, and then other arguments are also available. And then if I select the parentheses and stop typing, then I see the abbreviated version of this information window. And so I can say, what is the mean of of a of X, which is probably a series of numbers. Okay, I'm gonna delete that. So arguments can be anything, not just numbers or file names, but also other objects. Some functions take arguments that are specified by the user, or if left out, take on a default value, and these are called options. Options are used to alter the way the function operates, such as whether it ignores missing values or what symbol to use in a plot. However, if you want something specific, then you can specify a value of your choice. Let's try a function that takes multiple arguments, which is the round function. And here, when I stop typing, I can see that information window. It takes X, so it's expecting a numeric value. And it also has this argument called digits. And the default I can see is digits equals 0. So we want to round to 0 digits. So let's see the value 3.14159, and the default is to round this number by 0 digits. Here we've called round using a single argument, even though it takes 2 arguments. If we want more digits, we can modify the second argument, which digits equals, in this case, let's round to 2 digits. And when I run this line of code, we can see the difference now. You can also you can eliminate some code to shorten your code, because R recognizes that the first value is X and the second value that's provided is digits. So in this case, we actually we could eliminate the digits equals 2, because R recognized that this is the second argument that is signifying how many digits. I prefer being very explicit because I frequently pass my code along to people who don't have a lot of experience in R, and so I feel like being explicit helps the user learn R while they're going through it. So I recommend, if you're early in your R journey, to write out the arguments. If you do write out the arguments, then you can also switch their order. For example, I can tell R that I want 2 digits for the value provided. Okay. I'm demonstrating this so you can start to understand the flexibility inherent in R. But it's better practice to put the non-optional optional arguments, right? The values before you specify the arguments. Let's talk about vectors and other data types. A vector is the most common and basic type of data in R. A vector's a series of values. Those values can be numbers or they can be characters. We can assign a series of values to a vector using the C function. For example, let's create a vector of animal weights and assign it to a new object called weight underscore G, and for grams, we use the assignment operator to assign the following values using the C function. Inside the C function, it expects the values themselves. So in this case, I'm going to put a series of numbers, and this can be however long you would like. I'm going to Control Enter to run that line, and now I can see that this vector is stored inside our session, and it's a numeric vector of length 1 to 4. So there are 4 values. And if I call that object, notice how I use the tab autofill to reduce the amount of typing. When I run this object, R returns the output. A vector can also contain characters. So let's create an object called animals, and inside that object, let's use the C function to combine the series of names. When you're working with characters, you have to tell R that these are characters by putting them inside these quotation marks. So let's let's put mouse, rat, dog. I'm going to run that, and now it's stored. Here's a character, CHR, from a length of 1 to 3. So there's 3 values, 3 character values. The quotes around mouse, rat, and dog are essential here. Without the quotes are, we'll assume that these are objects. As these objects don't exist, there will be an error message. So let's look at what that error message would look like without the quotes, right? They almost look like objects, right? Like our weight G. And let's run that, and an error is returned, object mouse not found. So R is trying to interpret this, and it stops running the code at the first error because it doesn't know how to proceed. There are many functions that allow you to inspect the content of a vector or an object. For example, we can use length to tell you how many elements or values are there in a particular vector. I do length of animals as well. Another important feature of a vector is that all of the elements are the same type of data. So they should all be numbers, or they should all be characters. And the function class indicates what kind of object you're working with. Oops. So class weight, we can see as numeric. Class animals is a character. The function structure, str, provides an overview of the structure of an object and its elements. It's useful when you're working with large and complex objects like our neon data. So we'll want to use structure when we first import data to look at the different types of data inside that object. And structure animals. Let's run that as well. So it'll give you a summary of the object and its elements. We can use the C function to add other elements to our vector. For example, weight G. We can repeat the object name to add a new value. So here, add to the end of the vector. Notice how I could write the comment on the same line. That is acceptable or understands that. And now if I look at weight Chi, now it's a sequence of 1 to 5. So there's 5 variables in there. I can also add the value using the C function to the beginning of the vector. Add to beginning of vector by placing the value I want to add at the beginning. And now if we look at weight G, now we see those additional values added to our original vector. We can do this over and over again to grow a vector or assemble a data set. And this might be useful if you want to add results that you're collecting or calculating. We've been working with 2 atomic vectors. So character and numeric. And these are the basic building blocks that all our objects are built from. There are other types of vectors that include logical for true and false, and we'll start to use that when we want to tell our, are all these values greater than 5? and we want R to tell us whether that statement is true or false. And there are other vectors that we'll see later on. You can check the type of vector you're using, using the type of function and inputting your vector as the argument. So type of animals, we see that character. Vectors are one of the many data structures that R uses. Other important ones are lists, matrices, data frames, factors, and arrays. And you'll go through some of these in the Data Camp tutorial. Let's see an example of how we would subset vectors. This is useful when we want to extract one or several values from a vector. We need to provide one or several indices in square brackets. So square brackets are often used to subset. So for example, let's create a new object, animals, and we're going to store inside that object the values mouse, rat, dog, and cat. And because this object already exists, what R does is overwrite the existing value. So now we have animals, it's a character vector, and it has 4 values stored inside. If we want to select the second value inside our animals vector or object, we use the square brackets, and inside that bracket expects a number. So in this case, let's select the second value, which would be 1, 2. It would be rat. And now it returns the value of the second place. We can also use the C function inside our subset to select multiple values. So in this example, we use the C function. We want the third and the second values. So here we have 1, 2, 3. We'll give the dog, and 1, 2, the rat, in this particular order. We can also repeat the indices to create an object with more elements than the original one. So let's see more animals, a new object. Yeah. And I'm using the assignment operator. Inside that object, I want to store animals, and I want to store the first, the second, the third, the second object, the first, sorry, not the second value, the first value, and the fourth value. So see how I'm using the numbers to indicate what value I want, right? The first, second, third, or fourth. And notice how the length really doesn't matter. I can build this using however many values I want. And now I ran that line of code. Now I want the output. So see how this is the first value, the second value, the third value, the second value, and so forth. So our indices start at 1 because that's what human beings typically do. Other languages count from 0 because that's simpler for computers to do. Let's look at an example of a conditional subset. Another common way of subsetting is by using a logical vector. True will select the element with the same index, while false will not. So let's see an example of this. Weight grams is our new object. Inside that object, I want to store the values using the C function, 21, 34, 39, 54, and 55. I'm going to run that line. And then I want to subset on weight grams. I want to use the C function to provide a series of logical statements. So I'm going to tell R to subset true for the first position, false for the second. So I don't want the second, I don't want the third, I do want the fourth, and I do want the fifth. So notice how the positions of my true false are indicating what values I want from my weight gram object. So I want the first value, I don't want the second or third, and I want the fourth and fifth. Let's run that line. And so the first value, the fourth and fifth value are returned. Typically, these logical vectors aren't typed by hand, but are the output of other functions. So for example, let's see an example of let's put it up here so we can save it. And I want to return a true for all values greater of weight grams greater than 50. So R is evaluating this statement for each position inside of this vector, right? So it's asking, is this value greater than 50? That's false. Is this value greater than 50? False. False. Is this value greater than 50? True. Is this value greater than 50? True. And the return is a logical vector. You can combine multiple tests using the AND symbol, where both conditions are true, or the OR using the vertical line. Let's see examples of these. Let's say I want to subset values in my weight gram vector where weight underscore gram is greater than 30 and there's that and symbol, weight underscore gram is less than 50, square bracket. So I'm subsetting our weight gram vector so I want to return all the values where weight gram is greater than 30 and weight gram is less than 50. So greater than 30 and less than 50. Greater than 30, less than 50 would be 2. I expect 2 values. Let's see, or let's see, weight underscore gram. Let's subset on our weight vector for values that are greater than or equal to 30, or where the values of weight gram are equal to 55. Okay, three things that should be new. Right here we're using less than or equal to. This is the notation. Less than or equal to 30. Here is our OR. So now I'm asking R to evaluate whether the variables meet either of these conditions. I don't care which condition it satisfies, return values that satisfy either this condition or this condition. And the other novel thing is this equal to. So when we're signaling equal to by itself, we need two quotation marks. Two equal sign. Let me run this and notice that these two values satisfy either one of these conditional statements. So 21 is less than or equal to 30, and 55 is equal to the value 55. Okay? What happens when none of the values meet those criteria that you want to subset on? So let's say instead of less than or equal to, let's say greater than or equal to, or that weight is equal to 21. And instead of or, let's say and, because this or statement, all of the values actually satisfied it. So I want to give you an example of when no value satisfies these conditions. So I want to write and. So return values that are greater than or equal to 30 and equal to 21. And just by listening to that, there's no way that a value of 21 could be greater than or equal to 30. So for this statement, we expect no values to meet those criteria. When you're using, let's see an example of when you want to subset on certain character values. Let's create our object animals. Inside that animals object, let's store the values using the C function, mouse, rat, dog, cat. Remember, I need those quotations so R doesn't confuse these with objects, knows that they're characters. I'm going to run that line. Now let's subset from our animals object where animals equals cat, vertical line, which means or, animals equals rat. In this example, I'm asking R to return all values inside of our animals objects that are equal to cat or rat. When I run this line, R returns the values rat and cat. Let's see another example using the in notation. So let's ask R if any of these values are in our animals vector. We do this by calling the object using this in notation. So that's in followed by these percentage symbols. And let's ask, are any of these values inside goat? Rat, cat, dog, duck, goat. And when we run this line, R returns a logical values, false, true, true, true. What R is asking is, are any of these values in this first position? Do any of those values match? And no, so it returns value of false. Are any of these values in the second position? Yes, return value true. Are any of these values in the third position? We see dog, true. Any of these values in here, in the fourth position, cat, we see cat here, so it's true. In this final example, let's see how R handles missing data. R was designed to analyze data sets, and it includes the concept of missing data. Missing data is common in real data, and in R understands missing data as NA. When doing operations on numbers, most functions like square root that we started this lesson with return an NA if the data you are working with include missing values. This feature makes it harder to overlook cases where you're dealing with missing data. You can add an argument to a function to tell R to ignore missing values when you're calculating the square root or the mean. Let's see an example of this by creating a new object called heights. Inside that object, let's use the C function to provide a series of numeric values. And let's add an NA in there. And I pressed enter, but I didn't run it. Oh, now my heights is stored. And I can see heights, see heights. Okay, so it understands this is a numeric vector, and there's that NA in there. Let's try to calculate the mean of heights. Mean is a built-in function. And when I try to run this line, R returns a value of NA because it doesn't know how to calculate the mean where there's an NA, right? Remember the mean would be 2 plus 4 plus 4 plus NA plus 6 divided by the 1, 2, 3, 4, 5, divided by 5. And R doesn't understand how to calculate the mean when there's an NA. So instead, the mean and most statistical functions have an argument called na.rm for na.remove equals true. Now we're telling R to remove any NA values and calculate the mean on the remaining values. If I run this line of code, now R understands that the mean is 2 plus 4 plus 4 plus 6 divided by 4. If your data include missing values, you will want to become familiar with other functions like is.NA, where R evaluates whether the values inside of our objects are NA. And so it evaluates this. Is this first value NA? No, returns a false. But if we come down to the fourth value, is this fourth value NA? True, returns a true value. There's also na.omit, which automatically removes the NA value and returns an atomic vector of numeric values. Now that we have learned how to write scripts, and I'm going to save this now, the basics of R's data structures, we're ready to start working with data frames. In the next lesson, we'll learn more about data frames, and in your data camp tutorial, you'll see the vectors and objects again.